If KMeans feels like a magic box that sometimes groups points sensibly and sometimes makes nonsense clusters, it is hard to trust it. You will learn to see what KMeans is doing. You will watch how changing K and the starting centers reshapes clusters. You will learn a few simple checks that tell you whether a result is trustworthy. I'm Professor Pi, teaching AI foundations from basics to advanced, with simple, concepts-first Python that helps you solve bigger, real-world problems. KMeans is a tool people reach for when they need quick grouping. Imagine customer segments, sensor states, or simplifying a scatter of points into a few representative groups. KMeans is fast and easy, and it answers the question, which points are closest to the same center? It is not magic. It assumes clusters are roughly round and that Euclidean distance is meaningful for your features. When those assumptions fail, the labels still exist, but they may not mean anything useful. At a high level, KMeans alternates two steps. First, assign each point to the nearest center. Then move each center to the average of its assigned points. Repeat until things stop changing. If you start centers poorly or ask for the wrong number of clusters, you get poor results. We will build intuition with a tiny two-dimensional toy dataset. Run KMeans, sweep K, compare initializations, and then summarize cluster sizes so you can spot when the algorithm is lying to you. We will build a small interactive pipeline that shows spread, fits KMeans with two clusters, searches multiple K values by silhouette, compares KMeans++ versus random starts, and finally prints cluster sizes so you can see the distribution. These steps keep the math light and the insights strong, so the code stays approachable and the visuals map directly to intuition. This snippet builds simple 2D blobs and measures their overall spread. In this snippet, we create a synthetic two-dimensional dataset using a blob generator, which makes a few compact groups for us to play with. We also compute a simple spread measure to show how dispersed the points are. This often uses a function like pairwise distances or a variance calculation to summarize scale. The key lines set the number of samples and cluster centers for the toy data. Plot the points to confirm the shape, and print the overall spread so you have a baseline sense of how dense or loose the data is before any clustering happens. Now we will fit a basic two-cluster model and inspect its objective. This snippet runs KMeans with K equals 2 and reports its objective, inertia. This code fits KMeans with two centers to the toy data, so you can see the algorithm at work on the simplest, non-trivial case. The fit shows assignments for each point and computes inertia, which measures the sum of squared distances from points to their assigned centers and acts as the model objective. Important lines call the KMeans estimator with two clusters. Run the fit, and then print labels and inertia. If you change K to 1 or 3, the inertia will change predictably. Lower inertia is better, but by itself, it does not guarantee meaningful clusters. Next, we will search a range of K values and pick the best by silhouette. This snippet searches multiple K values and selects the one with best silhouette. Here we loop over a small range of K values, fit KMeans for each, and compute silhouette score, which measures how well separated and compact clusters are on average. The silhouette value combines within cluster tightness and separation from other clusters into a single metric between -1 and 1. Key lines run the fits, compute each silhouette, and record the best K by that metric. When silhouette rises and then falls, it indicates a sensible range for K. If silhouette is small for all K, the data may not have cluster structure that KMeans can capture. Next, we will compare how initialization affects results to reveal stability or fragility. This snippet contrasts KMeans++ versus random init to reveal stability. The idea is to run KMeans multiple times with two different initialization strategies and compare the resulting inertia and label consistency. KMeans++ picks smarter starting centers and often converges to better solutions with fewer runs, while random init can land in worse local minima. The main lines perform multiple fits for each init type, collect inertias, and optionally compute agreement between labelings. If ++ shows consistently lower inertia and higher agreement, your clustering is stable. Large variance across runs signals initialization sensitivity and suggests increasing the number of restarts. Next, we will summarize the final clustering by reporting how many points fell into each group. This snippet summarizes the final clustering by reporting cluster sizes. After you pick a final model, this code counts points per label so you can see if clusters are balanced or dominated by one giant group. The core lines take the labels array and compute counts for each cluster, then print or plot those counts. Seeing a tiny cluster and a very large cluster often points back to either an inappropriate K or to a mismatch between the data shape and Euclidean geometry. This final check is quick and often reveals whether the clustering result is actionable for downstream decisions or just a modeling artifact. Recap: KMeans groups points by iterating assign and update until convergence. Use it when clusters are roughly round and Euclidean distance makes sense. One caveat: KMeans can be very sensitive to the chosen number of clusters and to initialization. So always check inertia, silhouette, and cluster sizes. Wrap punch. One clear next step is to scale this exact pipeline up and add timing and accuracy checks. Run the K-sweep and initialization comparison on a larger dataset. Track inertia and silhouette against runtime, and increase the number of restarts to quantify stability. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.